Hi, everybody, and it's great to be here. Thanks a lot for having me today. So that's the agenda for today's session. Basically, we will start with a quick introduction to Kubernetes and what are the main factors that we need to consider when we need to ensure that Kubernetes applications are highly reliable, cost-efficient, and performant. And then we will look at the resource management mechanisms that Kubernetes put in place to ensure that applications are correctly managed and deliver the correct level of quality of service and reliability. We'll also look at the challenges that arise from making sure that Kubernetes applications are highly performant, cost-efficient, and reliable. And then we will see a new approach that we at Akamas have created using machine learning to actually get rid of all those kind of challenges and automate the entire optimization process for Kubernetes applications. We'll then have a look at a real-world example of using this approach in optimizing a real-life Kubernetes microservice-based application, and then we will conclude with some key takeaways. Just a few words about myself. So I'm a co-founder and CTO at Akamas. So I have close to 15 years of experience in performance engineering, capacity planning, capacity management, and basically that's it. So performance engineering has always been my passion and area of interest. So let's start with a quick introduction to Kubernetes. So I wanted to actually start with a funny story about how actually Kubernetes was born. So Kubernetes actually came out from Google, which always had immense challenges to actually optimize their own application, high traffic application like Google Maps and Gmail. So since the beginning, actually, Google had to invent a way to actually ensure those highly scalable applications were correctly, in a way, managed through fleets of hundreds and hundreds of servers. So the idea was to create actually a kind of platform, a highly distributed platform that was able to guarantee the scalability that those kind of high traffic applications required. So the internal name for this new kind of platform that were scaling this kind of container-based application was Borg. And it was very interesting to notice that it was kind of secret source within Google, and as it was considered one of the key reasons for Google actually being able to deliver this kind of high traffic application in a cost-effective manner. And it's very interesting that in 2013, actually, a couple of Google engineers actually wanted to, in a way, open source this kind of secret source system. And at the beginning, actually, from the story that we can hear here in this blog post from Google itself, actually, the idea was not considered very good, actually, from the internal, in a way, leadership team at Google. But eventually, the team had the green light, so the Kubernetes project was born, and they started actually creating the new version in a kind of open source fashion. So that's the way actually Kubernetes was born. I think it was very interesting. By the way, they recently also shared a Kubernetes documentary in a two-part, which actually tells the story in a deeper detail, which I definitely recommend watching. So that's how Kubernetes was born. Of course, Kubernetes now is being actually widely adopted pretty much across every enterprise for quite a variety of reasons, very, very good reasons. Of course, Kubernetes gives automated, in a way, deployment. It gives actually abstract infrastructure, so it gives workload portability across cloud providers and on-prem data centers. One of the things that I wanted to focus on is of course, on the performance side of it. So one of the main values is that, of course, Kubernetes takes care of scheduling all our application, containerized application into potentially hundreds or thousands of worker nodes to make the best use of available infrastructure resources. So to densely pack, in a way, all those containers into the machines, in the underlying machines. But at the same time, it has built-in capabilities actually to ensure that those applications do not in a way, interfere among each other. So Kubernetes provides capability to actually guarantee performance isolation among applications. So that's the kind of capability that the platform provides, the kind of promise that Kubernetes is making on application developers, which is actually very interesting and very compelling. So what is very interesting is that if we look at the adoption of Kubernetes, one report that came out last year from the FinOps organization is that Kubernetes costs are actually on the rise. So this report actually did a survey among very mature organizations that are actually adopting Kubernetes. And what they found out is that, of course, pretty much the vast majority of the respondents actually reported that Kubernetes costs are on the rise pretty significantly, also close to 20%, and year over year. And what is very interesting is that what are the reasons for these cost increases? So the report, of course, comment about the fact that, of course, Kubernetes is on the rise, the adoption, so it's pretty natural that costs are increasing. But also they are actually, in a way, considering the fact that there may be quite a bit of inefficiency in how people is managing Kubernetes today. So part of the reason why those costs are so highly rising is that, of course, it's not very easy, actually, despite all those capabilities that the platform provides, to make sure that applications are run in the cost-efficient way possible. And that's one of the, in a way, interesting data point that we are starting to see on the market. And of course, we will discuss a little bit more in the when we talk about the resource management, how that is, why that is the case. But it's not only cost, actually. So if you look at the early adopters of Kubernetes, again, quite a bit of very mature and highly skilled organizations in the Silicon Valley area, most of them. Actually, we see that they experience quite a bit also of performance and reliability issues in the Kubernetes, in the applications running on Kubernetes. So they even created this very interesting website, which is called Kubernetes Failure Stories. It was created by a Zalando engineer, actually, which actually was meant to, in a way, kind of share all the incidents and failures that people had while running on Kubernetes, with the hope of actually learning from each of them and improving the status of the platform itself. And what is very interesting is that, again, we will see the reason why in a bit, but due to the way that Kubernetes works, in a way, lots of engineers and lots of application developers found some pretty counterintuitive situation where the application performance actually suffered, like for example, high latency or CPU throttling, so lack of access to this underlying platform resources. And it's not just performance issues, but it's also stability issues that may arise, like, for example, out-of-memory kills. It's one of the reasons. We will see what it means in a couple of slides, actually. So the fact that application may get killed while they are running if they, in a way, consume too much resources. And that is another kind of potential, in a way, outcomes of not properly configuring our application on Kubernetes. So that's kind of the issue. So we see that people are facing both cost on one side, cost issues, and on the other side, performance and stability issues when running application on Kubernetes. So the key question at this moment is actually, what is the reason why it is so? So why Kubernetes that provides such a great set of capabilities for running high-scale containerized native application, why people is in a way finding it difficult to actually make sure the application are actually cost-efficient and reliable and highly performant? That's the main question. So in order to answer this question, we need to actually go a little bit deeper into how Kubernetes actually is managing the resources of the containerized applications. So let's have a look at some key facts here. So the first key fact, which is very interesting to understand, is the concept of resource request. So basically, resource requests are the resources that a container is guaranteed to get. So when an application developer needs to run a Kubernetes application, it has to define this YAML file, which is kind of represented on the left here, where it has the ability to say, okay, for CPU and memory, how much resources should this container always get? So as you can see in this example, this is an Nginx container within a given pod, which is the unit of scheduling within Kubernetes. And for this Nginx container, which is our application in this example, basically we are requesting 2 CPUs and 2 GB of memory. So when we ask Kubernetes to schedule this container, Kubernetes will actually consider this amount of resources in order to understand where to run this pod, when to run this container across the infrastructure. So as you can see in this example, a Kubernetes scheduler will find a node. Let's say that we have a node with 4 CPU and 8 gig of memory, which initially is empty. So we find a node that actually is able to host this amount of resources. So a node that has 2 CPUs, 2 free CPUs, and 2 gig of memory still available. So in this case, in this example, let's say that pod A gets scheduled on this node. So let's now assume that another pod comes and needs to be scheduled. Again, let's assume that this other pod again requires 2 CPUs, and this time it requires 4 gig of memory. So this pod B, you can see in the picture, it's the blue one. Is again, it may be scheduled on the same node as the node still has some capacity available both from the CPU and memory perspective. So in this situation, actually, if another pod should come, let's say pod C with pretty much the same amount of resources, it won't be scheduled on this node because actually, as you can see, there are no more CPU resources left. So Kubernetes will find a way to find other nodes, other infrastructure that has this kind of level of capacity required that is still free. And if it is not able to identify a new node, basically the pod won't be scheduled on the cluster. So what is the main takeaway here is that, of course, resource requests are very, very important from a cluster capacity management perspective, because actually it's a key concept that the Kubernetes itself is considering in order to understand when and where actually it should actually allocate a pod. So the other consequence of that is there is no really overcommitment on the resource request. So with respect to other technologies like we might have in mind, like virtualization, where actually we might schedule many more virtual machines on the same, with many more virtual CPUs, for example, with respect to the number of physical CPUs that were available in the host. That's not really how Kubernetes was designed to work. So actually, there is no overcommitment as regards the request. So once we have, in a way, allocated the number of available capacity in terms of requests, there is really no more, in a way, no more application that can be scheduled on the cluster. The other consequence that of this fact is that the whole topic of Kubernetes capacity management is basically done via resource requests. So it's basically done via a kind of allocation mechanism. So resource requests are the amount of resources that a pod actually allocates, actually requires, and it's totally unrelated to the amount of resources that the application actually uses at runtime. So what does that mean is that, for example, we might very, very easily end up in a situation where our cluster is actually fully allocated in terms of requests. So there is really no more space to allocate more application. But at the same time, the cluster may be highly underutilized. So it may be even a 1% utilization of CPU, while still from a Kubernetes and management scheduling part of view, the cluster will be considered pretty much capacity full. So that's one of the in a way key concept, because actually based on how we allocate the resources of the pod, and especially related to requests, of course that's one of the main ways that we can drive and we can manage also the cost of running our application, which as we have seen, is one of the issues that people using Kubernetes is experiencing today. So the other concept, which is very interesting, is that it's resource limits. So as we have seen, resource requests are, in a way, kind of allocated amount of resources that we require to be available in the cluster, but actually the container can consume more resources than the request. So the resource limit is actually the way that Kubernetes provides to application developers to specify the maximum resources that a container can use. So when a container actually, when we say, for example, CPU limit equal 2, this means that the container cannot really consume more than 2 CPUs. And if it tries to do so, actually, if a container tries to actually go above the resource limits, bad things can happen. And what does it happen is actually a function of the kind of resources that is being utilized. So if we are talking about CPU, so if a container actually tries to use more CPUs than the limit, basically Kubernetes starts to throttle the container CPU. So this means that actually the container will see a kind of a CPU slowdown. So the access to the CPU will be actually in a kind of paused for a moment. Let's say we will see how that what does that mean in the next slide. And the result of this effect will be most likely an application performance slowdown. The other thing that is very interesting, which is kind of more important in a way, more as regards the application stability at least, is what is happening when the application starts to hit limits in terms of related to the memory. So when memory usage actually starts to approach and hit the limit, Kubernetes will actually adopt a pretty drastic kind of measure, which basically will mean that the Kubernetes will kill the container. So basically, again, that's pretty, in a way, counterintuitive or unexpected if we think about virtualization world where, or traditional operating system memory management, where this kind of situation is being treated with a kind of swapping mechanism. So basically, again, the application will slow down, but it will still be, in a way, alive, depending on the severity of the situation, of course. But Kubernetes actually policy is kind of more strict here. So as soon as the amount of resources that is being used, the amount of memory being used hits the limit, the application will be killed. So again, this can have pretty significant stability issues for the application itself. The fact number 3 that I wanted to highlight here is a kind of, in a way, effect of the CPU limits that we had talked about before, which actually is a kind of very interesting and somewhat unexpected effect that can result with especially with Kubernetes. I would say it's kind of not that well documented. There are some, in a way, information on the web about this effect, but I wanted to stress it here because it's very, very interesting. So we have mentioned the fact that when CPU usage, in a way, approaches the limit, the Kubernetes starts to slowing down to throttle the CPU access, basically. But what is very interesting is that, of course, when this kind of phenomenon is starting to happen, so it's happening like, I don't know why, when the CPU is I don't know, 90% close to the limits, or is it happening before? So we have started this approach with this process in our labs, and we have done lots of benchmarking with different applications to understand when the CPU throttling starts to happen, also studying different kind of application with respect to the CPU limits. So we measure the CPU usage. We did lots of benchmarking with increasing level of CPU usage with respect to the limit. And then at the same time, we measure CPU throttling. And what we discovered was pretty interesting and unexpected is that CPU throttling can happen pretty early. So when CPU usage is up to 30% of the CPU limit. So actually, that was not what we expected. We expected much more, something like 80%. So when we are getting close, we start to be throttled. But instead, we have measured the fact that throttling can happen pretty early in this process. And that can, of course, be a source of kind of unexpected and sudden latency spikes, for example, in Kubernetes application, which is actually something that we see a lot also in our customers. And it's something that might be kind of hard to explain by looking also at the observability tools. But that's one of the main kind of reasons. Why is that happening is due to the way that CPU throttling is managed at the Linux kernel level. We won't go deep here, but feel free to reach out if you want to know more. And that's on the right, you can see an example where actually people have tried to actually remove the limits and see what was happening to the service latency. That's an example that was published by Buffer Inc., which is an internet company basically that is running their services on Kubernetes. And what you can see here is that the latency of the service over time, and then you can see that basically the latency starts to drop near zero when they actually remove the CPU limit. So the thing is that CPU limits seems to have this kind of pretty important effect on performance, especially high percentiles in terms of latency. So the main question that arises in our mind would be actually, should we get rid of CPU limits? So why don't we simply why don't we simply use CPU requests, which is important to let the CPU, the Kubernetes scheduler understand the amount of resources that we need, and we won't actually use CPU limits, we get rid of limits. Actually, that's actually not a best practice, and here you can see that also Google recommends always setting both requests and limits, because actually limits, if you remember, about the key point of Kubernetes ensuring on one side efficiency, but also performance isolation among the application. So if we run without limits, a single runaway container may may basically bring down our most business critical application without anyone noticing. So it's a very dangerous. So for the stability of the entire Kubernetes platform, it's actually very important to set both requests and limits, and that's again a best practice that also Google recommends. So basically, we are left with this kind of challenge of actually properly setting resource requests and limits on one side to, of course, to not to waste money, because we might over allocate the resources on the cluster, and on the other side, not actually have performance and stability issues that may result if those configurations are not set properly. Well, another key interesting fact that I wanted to bring up here is that, of course, as we have seen, we have, in a way, we have seen that those kind of settings, CPU requests and limits, are very, very important basically for the success of running Kubernetes applications. But on the other side, basically, it's very, very hard for people to understand how to set those parameters. So the answer from the Kubernetes project, and that we see on, again, as a key recommendation, is to help users set those kind of parameters, is to leverage Kubernetes autoscaler. So in particular, the vertical, Kubernetes provides actually more than two autoscalers. As regard the setting of the pod request and limits, the autoscaler is that Kubernetes provides out of the box is called the VPA, which stands for Vertical Pod Autoscaler. Vertical means the amount of resources that a single container is allocated. You may remember also that Kubernetes also provides the horizontal pod autoscaler, which has more in a way, the goal of ensuring autoscaling, which is replicating the pod based on the traffic, which is not in scope for the moment in our story. So let's focus on the VPA. So the VPA basically provides a way to, in a way, suggest the recommended CPU memory request for a pod based on the actual usage that the pod actually should measure, that the VPA can measure while the pod is running in production. So the thing is that we have kind of mixed experience with the VPA, so, and that is mirroring also what the industry is finding out. And I wanted actually to highlight here a kind of experience that we did, where we basically took a microservice container running a microservice application in Kubernetes, which were, in a way, was subjected to a typical production traffic, so daily diurnal pattern, as you can see on the service throughput chart here on the top right. So that's the traffic that we actually injected to these, we generated to this pod. And you can see here on the top left the response time of this pod. So you can see basically 90 percentile latency. On the other chart here shows the actual CPU requests and memory requests that were actually assigned to this pod. And here on the bottom right, you can see the resulting CPU utilization and memory utilization, which is actually the actual usage, for example, of the CPUs with respect to the limits, which were set in this case equal to the CPU request. So the key thing to notice is that in the first period, we actually ran this load test where the VPA was turned off. So it's basically the container had these 200 millicores assigned for for the CPU and close to 450 meg for the memory. So that was the original allocation of requests and limits and CPU and memory requests for the container. By the way, the limits were set basically equal. And you can see actually the kind of the SLOs that was kind of being breached a little bit when the traffic was higher. And then what is very interesting is that we turn it on in this moment. We turn it on the VPA. So the VPA actually looked at the past utilization of this container, and then actually based on the utilization, the VPA decided that the container was kind of over-allocated. So it pretty much cut in half the amount of CPU requests that was assigned to this pod, and pretty much did pretty similarly to the CPU to the memory request. It was actually reduced close to half. What is very interesting is that as a result of this decision, which was pretty purely in a way done looking at CPU utilization of the container over time, as you can see, the latency of the container pretty much skyrocketed. So that's, by the way, a logarithmic axis. So the container, the latency response time P90 is now close to 1 second, while it was 128 milliseconds before. So close to 10x worse performance as a result of the suggestion that the VPA did. So the VPA did actually, it's a kind of initial answer from the out of the box that is available, but we are finding out that it's kind of not working very well to ensure performance of the application, cost efficiency, and reliability. So that actually concludes pretty much the challenges that we see on Kubernetes. So properly setting resource requests, properly setting resource limits, also the replicas and autoscaling. We didn't touch on this point, but also that's another area where you need to actually pay a lot of attention of the configuration, which kind of metrics do you use for autoscaling, which kind of threshold. And that for each container, you typically not only have the Kubernetes settings, but you also have the application settings like the JVM, if you are running a Java application, for example, which kind of garbage collection are you using, which kind of heap settings do you have there, but also there may be Golang settings, GoGC, for example. It's another similar tunable that can provide interesting benefits for Golang application, but you may also have application-specific configuration like the application server, etc. So the key thing to realize that, of course, moving from a kind of monolithic architecture to a microservice application architecture, you will have dozens of microservices all interacting in order to provide a kind of business service with its own performance and availability SLOs. So the real-life optimization challenges become actually even harder with respect to what we have seen till now, where we have looked just at one Kubernetes container, but we need to really multiply that according to a number of the, tens of microservices that might be running our business critical application. So that's a challenge that SREs and performance engineers and developers have today. And today, these kind of challenges are pretty much solved manually with a lot of try and error approaches, perhaps doing load testing and understanding what are the bottlenecks, or other times just observing with observability tools how the application are running in production and trying to optimize and to improve the resilience, etc. The process that we use today is highly manual. Of course, it's time consuming, it's complex, because actually the problem is very, very complex. So the idea that we have at Akamas is actually to try to bring these new these capabilities, these processes of optimization to kind of new levels, where actually we kind of move away from a world where we as experts, as performance engineers, as SREs and developers try to fiddle with the stack and try to tune all those configurations manually and try to see what is the effect, with a new world where actually we have autonomous systems that are actually much smarter than us and actually are able to optimize the application in a kind of much more effective and time efficient and cost efficient way. So this approach is based on a kind of 4 new requirements that we have identified. So on one side, it's full stack, meaning that it's not just about tuning the resource request of, I don't know, one layer of Kubernetes. Kubernetes is just one layer in the stack. We also have the runtimes. We may even have databases configuration. We may have big data configuration. We may have, I don't know, instance types on the cloud that we might choose from. So it's the whole stack is actually composed by many layers. And if you really wanted to solve the problem, we don't just need to, in a way, to solve to properly optimize just one layer, but it is important to actually optimize end-to-end the entire stack, because it's what our actually at the end of the day, our enterprise application runs on top of the entire stack. So we need to make sure all the layers are optimized in a kind of holistic way. Smart exploration is important because if you think about the number of knobs and configuration options that we have in the stack, it's huge, as we are talking about, and they are all interacting among each other. So it's very complex for the human brain to reason about this space. So the idea is that we need kind of help in a way to explore this huge space on configuration, and that's where we use AI to actually being able to identify the best configuration in the most cost-effective and time-efficient way possible. The third pillar, which is very important, is that our optimization is goal-oriented, meaning that the goal for this optimization can be defined by the user. So it's not just about, I don't know, making Kubernetes more efficient, but sometimes our goal is, let's improve our reliability of the application. Let's make sure that we have the minimal amount of cost on the cloud while still matching performance requirements and SLOs that we have on throughput and error rate and response time, something like that. So the goal of the optimization is more complex than just simply let's reduce CPU, the allocated CPUs, because all those parameters at the end of the day impact also application performance. So we must have a way actually to define what is our end goal, which is realistic for the needs of modern performance engineers and SREs. The fourth pillar is pretty important because also we wanted to automate as much as possible the entire optimization process. As we are going to see, it's not about the platform saying, okay, you are gonna and you are getting close to the amount of memory assigned to your container. You need to find out to do something, but our platform aims at actually suggesting and also autonomously fixing the configuration problems and apply the configuration parameters to the live system. So we are going to talk a little bit more how this approach works in a minute, so that the entire process gets automated as much as possible with a proper level of control, of course, for the humans and for the SREs that need to, for example, approve the configurations, etc. So that's the high-level approach. So at Akamas, we have actually designed an optimization platform that we call an autonomous optimization platform that can actually support, that implements this kind of new approach with a kind of autonomous optimization process, like we say. So it's not, in a way, let's move away from a world where engineers tune these applications manually and see the results, kind of time-consuming, error-prone and lengthy process, to a world where we have an autonomous system that is capable of providing these optimization services that can run automatically based on the objectives that the user can define. A typical important question is, do we work on pre-production or do we work in production system? The answer is that we support both scenarios. So you can see here the proactive optimization is what the kind of optimization process that we typically put in place before the application gets released in production. So that might include different scenarios where, for example, I have a change in the architecture. I want to upgrade change my cloud provider. I want to upgrade my technology layers, or even I want to evaluate a new design of the application. Let's try to make sure that my application has the proper configuration optimized for this new change. It might be, for example, a JVM change, an upgrade on OpenJDK, or a change in a library, pretty critical library, etc. I wanted to make sure that all my configuration of the application are optimized before releasing to production. Other scenarios may be, I am expecting a peak in the workload, typical example is the Black Friday. How do I make sure that my application is correctly configured to handle this kind of peak actually before the event occurs? So I may leverage load testing in pre-production environments and leverage load testing and approach like Akamas to make sure that our configuration for the autoscaling, for the containers, for the JVM, for the replicas, whatever you need, are properly configured to make sure that this will happen smoothly. Other typical scenarios may be also the chaos engineering, where that's a big trend today. Chaos engineering, we might for example, highlight an area where we might focus in order to improve the resiliency of my application. For example, we need to set up more replicas, or we need to set up the auto-scaling system to make sure that application can sustain load in the face of failures. Of course, this comes out, and this implies being able to select properly, configure those elements of the auto-scaling of the runtime, etc. And that's where Akamas can help automating all those configurations. The live optimization is something also very interesting, because we can also, in a way, optimize the application when they have been released in production. So when they run, when they are subjected to the real life user traffic, and that's very interesting, very exciting capability that we are offering. So in this case, for Kubernetes application, for example, we may adjust the Kubernetes resource limits and also the runtime, like the JVM, based on the traffic that is running on the application. So it becomes much more, in a way, dynamic and runtime. That can be also based on a human approval process. So the user can evaluate recommendations that are, in a way, provided by the platform. They can review it before applying to the production environment. Or even the next stage for us is actually the platform will be fully autonomous, and that once the user, in a way, gets accustomed to the recommendation, he can actually switch to a fully autonomous mode, where Akamas is constantly optimizing the application live in production as they've been subjected to the different traffic that is happening. So that's the general idea of the platform. So let's now see how actually ML comes in, because actually our optimization cycle is based on 5 phases. So the first phase is we need to apply a configuration. So phase number 1, of course, Akamas is not only, in a way, to suggest a configuration in a dashboard, but it aims at automating the entire process. So the first step is really we need to apply a configuration that gets suggested to the system. So again, we can do that by leveraging whatever configuration management tools you may already have, like Terraform, Ansible, Kubernetes APIs, etc. So that's the idea. We don't have any agent, but we rely on what configuration management tools typically customers already have. Second step is what is called here apply the workload. So based on the scenarios, if you are working in pre-prod environment, that may mean triggering a load test that replicates a realistic workload, so that the application is stressed properly, and we can see and we can actually measure if a new configuration is, in a way, is improving our goals, or it is actually making worse, and how it needs to be adjusted. But while we are running in production, basically we don't need any application, any workload to be applied, because actually we simply observe the application as it is running in production while it is processing the real life user workload. Step number 3, we collect the key performance indicators, which means performance metrics and all the metrics that we are interested in. Again, no, we don't provide any agents, but the idea is that we collect metrics from the typical observability tools and monitoring tools that customers already have, like, for example, Dynatrace or Prometheus. And the first step is that once we have collected all those metrics, remember, Akamas is a goal-driven solution, meaning that, of course, you can define your goal, which may be even a combination of metrics, like, for example, efficiency metric like throughput divided by CPU usage. So the first phase is where those goals and those metrics the experiment gets scored. And the fifth phase is where really machine learning kicks in. So we won't deep dive into the machine learning piece in this session, but I want just to comment a little bit on the kind of approach that we use, because it's a typical question that we receive. We use reinforcement learning, so meaning that, of course, our AI needs machine learning needs to actually interact with the environment. So it actually applies configuration, so it changes the environment, it applies the configuration to the environment, then we measure the result, which is called reward in the machine learning, the reinforcement learning language. And then actually we decide what is the best configuration, the next best configuration to apply. So the process is kind of iterative up to a kind of budget that can be defined. And the machine learning actually continuously learn how the system needs to be optimized, even in the presence of dozens of parameters. The machine learning can understand what are the best parameters to tune, what are the best region of this use space, which we might visit in order to improve the performance or resiliency, whatever. So in these new processes, it's important to actually understand that, of course, the performance engineers, the SRE, and the developer is still in the picture. So it's not something like a magic system that automates everything, but the role of performance engineer, developer, and SRE is still key, because, of course, they need to define the optimization goal. They need to define the constraints, like I have my SLOs, response time error rates that I don't want to, in a way, to make worse, etc. And then the system can actually automatically tune the target system as we have described, and the output is really actually an optimized configuration that, in the case of pre-production environment, we can later on promote to production, or in the case of live optimization, it's basically automatically applied to the system. So the result that we get is that our systems are constantly being optimized in order to ensure that they are cost efficient, the performance and reliable according to the goals. So that's the approach at the high level. So I wanted also to provide you a real life example in order to let you better understand how this process actually plays out in a kind of concrete example. So the example that I wanted to show you here is based on Google Online Boutique, which is a typical microservice application by Google. So it's basically composed by 10 microservices that feature a modern software stack. The application is open source, and it also includes within the repo, you can also find a load generator, which is very handy, based on Locust, which basically is able to generate kind of realistic workloads, and that are basically users that are visiting and doing purchases on this store. So the architecture is basically shown here. So you have in the central part of this picture, you have the Online Boutique application, which is, again, 10 microservices running on Kubernetes. As regard the optimization, you can see that we are optimizing in this example with Akamas 22 parameters, which are basically the CPU and memory limits for each microservice. So they are 22 and not 20, because actually we have 11 containers, because there is also a database in there in one of the microservices. So basically we have 22 parameters. That is the scope of the tuning. And we tune the application as it is being subjected by real-life workloads by Locust, as we have mentioned. As regard the way that we change the parameters, we leverage basically Kubernetes API. So basically we change the deployment of those microservices where you have those values written in. And then we also measure the microservice performance and the actual resource usage, leveraging basically Prometheus and Istio. That's the idea. And what is very important is when we do optimization with this kind of a new approach is the capability to, in a way, declaratively define the goal that we wanted to achieve, as we have said. So the nature of Akamas being goal-driven, you can see it here in a way in practice. So in this case, we wanted to maximize the cost efficiency of the application, meaning that we wanted to maximize the throughput. As you can see, the metric is that we're measuring the front end, which is where all requests are being processed. So you have the success transaction processed by the front end as measured by Istio, which is a service mesh running on Kubernetes. And we divide that by the application cost. The cost is basically, what is the cost of running this application on the cloud? So it's related, of course, to how big are the containers, which is the parameters that Akamas is tuning. What is very interesting is that we also set constraints because, of course, we don't want to make the application run slower, or we don't want to make the users see failures. So again, you can see the power of the goal-driven nature because we say, okay, we want the application cost less, but we don't want to have errors, or we don't want to have higher response time. So that's the way our goal-driven approach works. And you can see here basically the results. Once you have defined those kind of high-level configuration within Akamas, we can press play and Akamas start tuning the platform. And you can see in this chart basically the progress of this optimization over time. So each dot in this chart is a different experiment, as we call it. So it's basically a different configuration of the parameters. So remember the 22 parameters, CPU and memory for each container. Each dot is a single, in a way, allocation of CPU and memory for all the containers at the same time. So machine learning is able to change them at the same time. And you can see that the first dot is the 0% is basically the baseline configuration, so the initial configuration of those containers as per the open source project. And you can see that over time, basically the score starts to improve. So the score, again, remember, is throughput divided by the cloud cost. So we wanted this number to be higher, so we want to maximize. And you can see that we reached that pretty significant 77% improvement in the cost efficiency of the application just by touching the configuration options, and by the way, without any performance degradation, because each dot actually is respecting our SLOs in terms of response time and errors. And you can see basically that the whole optimization process was also very fast. So it took the platform about 24 hours to completely autonomously tune the 22 basically containers, 11 containers running in this application. So this is pretty interesting with respect to the manual process that we typically use. If you look at in a way the best configuration, that's a critical question. Sure.
So about the previous slide, so did you measure the cost for actually doing this machine learning based approach?
Yeah, that's a great question. Yeah, we can do that. Actually, you can decide the kind of time, the budget that you leverage, that you assign to the optimization. So actually, you can for example, say, I want to just run this weekend, I want to run for this amount of iteration. So you have these ways to actually, in a way, limit the time and the budget that you use for the optimization process. Of course, it's typically very, in a way, a good ROI exercise, because once we have found out the configuration, that's what the application runs in production. So it's where the biggest savings actually may be realized. Okay, so that's the optimal resources. So how can actually Akamas achieve this kind of result? You can see here for each container, actually, basically, Akamas reconfigure the number of CPU and memory requests and limits. You can see basically here in the two colors, the baseline, the orange one and the green one, it's the best. So what is very interesting is that machine learning and Akamas autonomously learned that in order to improve the performance and the cost efficiency, it had to pretty much decrease the CPU limit set for almost all containers. And that is very kind of smart move, because CPU, of course, is the biggest cost, in a way, ratio, the biggest cost driver of running the application on the cloud. So actually, machine learning automatically learned that during experiments. But as you can see also, machine learning didn't simply decrease the CPU, because that would lead to a violation of the SLOs. In fact, actually, for two specific microservices, machine learning actually figured out that it had to increase the amount of CPUs, because, for example, that may become bottlenecks and violate our SLOs. What is important to realize that with this process, is basically that's the best configuration that we can get, and we can analyze, for example, before applying to production, without having spent pretty much any time doing this kind of process ourselves. So pretty much the process may be have been around for 24 hours, and at the end of the optimization process, the performance engineer or application developers get this kind of picture that is the result of this optimization that is still matching the SLOs and improving the cost. So what is also interesting is to see what is about the performance over time of the application when we apply this new configuration. So you can see here two charts that are coming from directly from Akamas, where we compare the over time, the baseline, and the best configuration in terms of service throughput on the left and response time on the right. So basically, those are two experiments. You can see it's about half an hour performance test, and you can see the transaction per second of the baseline, which is the original configuration. And you can see that despite this configuration improving the cost, it also increased the throughput basically by 19%. You can see the experiment number 31, which is actually the best experiment, is improving the performance over time. But it's also very interesting to see the improvement on the latency. So the original configuration actually had a pretty erratic behavior in terms of latency. Akamas find out that actually by reconfiguring all those options, the performance of the entire application, end-to-end application, was made much better by adjusting those parameters as well. So that's about it. So I want to just to conclude with a few takeaways, and then we'll leave space for your question, which I'm very happy to answer. So the key takeaway is that, of course, IT is getting more and more complex. That's what we all know, and in particular, Kubernetes applications are actually not the exception. Quite the opposite, meaning that lots of teams are having a hard time to actually make sure the applications in Kubernetes are actually cost efficient, reliable, and performant with respect to the traditional monolith. So that's an important challenge that we are working on, and we are seeing on the market. Our new approach is basically a way to actually automate the process that is today largely manual towards a kind of new approach that we call autonomous performance optimization, which is leveraging machine learning actually as a way to not substitute, but actually as additional tools in the performance engineer or SRE developers tool bag, and actually to improve the situation. And the actual benefits are actually with these kind of processes, we can really make sure our services are cost in a way optimized for cost efficiency, for throughput, so they can consider, of course, we can actually make sure that we deliver those services with the best possible reliability by incorporating also our SLOs. And the beauty of that is that the entire process becomes largely automated, so we don't spend huge efforts and in a way lots of resources of the typically application teams for doing this kind of exercises. That is it. Just really, actually, I forgot that we have one last slide. If people is interested in Akamas, you can try out Akamas. We have a free trial on our website with a kind of a lot of exercises that and the self-service guides that you can use with a kind of step-by-step approach to try out the platform in your own environment. So that is it. And thanks a lot for your time, and I'm happy to answer any question you may have.
Thank you very much, Stefano. And thank you for everyone for joining. Last chance to ask questions. Okay, so let us thank the speaker. And thank you, Stefano. It was very interesting.
Thanks a lot. Again, thanks for having me. I really enjoyed the session. Talk to you soon, guys.
Bye. Thank you.
Bye.